Okay, welcome back. A reminder of where we were last time. So we discussed how we define and measure reaction rates. We talked about the factors that will affect how fast a reaction occurs. Um, and now we're getting into how we think about and visualize the way reactions happen. So last time we discussed energy diagrams. And so energy diagrams look something like this. You have a reaction. You start out with reactants that are separate. You start to break old bonds and form new bonds, and the energy goes up. You reach a peak that we call the transition state. And then from that peak, you slide down to the products and you complete the formation of new bonds and the breaking of old bonds. Okay. So that's a reaction coordinate diagram. It can tell you the activation energy of a reaction. So the higher the hill, the bigger that energy barrier for the reaction to occur. And it can also tell you the change in energy for the reaction. So whether the reaction is endo or exothermic. All right, today we're going to get into what's actually going on between atoms and molecules. All right. And that's what we call a reaction mechanism. The vast majority of reactions that we're familiar with don't occur all at once. So there's going to be a sequence of steps, and we call that sequence of steps the reaction mechanism. All right. So here's a simple example. Again, we're going to use lots of fictional examples just because they make our lives easier. So I have a molecule of A and two molecules of B, and they're going to come together and make AB2. It's really unlikely for that to occur all at once. Why do you think it would be unlikely for this to occur all in one collision? Remy? All right, the odds that all three molecules bump into each other in the right orientation at the same time, the odds are astronomically low. And so reactions generally involve either one particle or two at a time colliding. Did we get frozen? All right, we're back. So that fictional reaction might occur by a series of steps. You might have A bumping into B and forming a molecule of AB. And then that molecule bumps into another molecule of B and forms AB2. All right. This could be our reaction mechanism. Two steps. Form the first bond, then form the second bond. Note that if you add these two equations, if I were to just put a line at the bottom here and add them together, I get A plus B plus AB plus B makes AB plus AB2. And then how would I simplify that equation that I just wrote? What things might I put together? I can put together the B's and make that 2B. And then I have AB on both sides of the equation. Well, what can I do when something's on both sides of an equation? Cross it off, get rid of it. So a reaction mechanism, if you add the steps together, they should add up to the overall reaction, which they do in this case. Okay. Every step in a mechanism, when we write a mechanism, every step should represent what we call an elementary step. An elementary step occurs in a single collision. Okay. So when we talk about a reaction mechanism, we're really breaking down an overall reaction into what series of elementary steps make it up. Yep. All right, so question is, if we go back to the energy diagrams, if there's a two-step reaction, would the reaction coordinate diagram look like this, or would there be two bumps? And the answer is yes, there will be two bumps. So that we'll talk about again in a minute. What I've drawn for a reaction coordinate diagram was for a single elementary step. But if there's more than one elementary step in a mechanism, there will be multiple bumps along the way. All right, so here's a mechanism. Here's a reaction. Actually, before we do that other example, let's stick with this simple example. Is this the only possible mechanism I could have written for this reaction? A plus 2B makes AB2. All right. Propose a different mechanism. What would be a different mechanism? So I said one possibility is A combines with B first, and then AB combines with another B. What's another possibility? All right. Another possibility is B combines with B first, and then B2 combines with A. There are lots of other more complicated possibilities we could come up with. But these are the two probably simplest mechanisms we could imagine for that reaction. So in the next slide, I give you an example of a real reaction. I want you to propose two different potential mechanisms for the reaction on the next slide. So the question is, does it have to be only two steps, or could it be more? It could be more. I think the fun thing about mechanisms is you can imagine lots of possibilities. All right, share at your tables what mechanisms you've written down. All right, Adam, what's a mechanism that got proposed at your table? Oops. All right. F plus F makes F2. All right. All right. So this first step you wrote, F plus F makes F2. The problem with that is, do we need that to make up this reaction? No, because this reaction starts with F2. So I'm going to take that part out. All right. But the second step certainly could be part of it. So your first step might be a molecule of F2 combining with a molecule of NO2. What might happen next, Remy? All right. So we might have first F2 and NO2 combining to make NO2F2. So it's like the two molecules just combine. And then another molecule of NO2 comes by and grabs one of the F's away. So we end up with two molecules of NO2F. All right, that's a feasible mechanism. What else? So the question is, are you allowed to have charges that wouldn't necessarily work? Well, it's not that there are charges that don't necessarily work here. So the question is, would NO2F2 be a stable molecule? Well, now we'd get into drawing Lewis structures. And it might be challenging to draw a Lewis structure that would work for that. Here, I could come up with one, I think. Maybe. Here, it's going to have an odd number of electrons. And so it's going to have to be a radical. So I think it's going to have to look like this. Could work. Remember, NO2 is a weird molecule to begin with because it has an odd number of electrons. And so this NO2F2 is also weird. So that might be a reason not to expect that mechanism. But right now we're just kind of throwing ideas out there for how this might happen. And so this is a viable option. What other mechanisms came up out there? Ralph? Okay, again, I don't want to start with N plus O2 because I already have NO2. So my mechanism should start with the things that are on the left side. So start with NO2. Okay. Well, you want to give it, so NO2 plus F2. That was your first step. NO2 plus F2. All right. What could that make instead of just combining the two of them? What would be another option? So in this first proposed mechanism, we just combined NO2 and F2. What could be different here? All right, this could make NO2F plus F. So in other words, the NO2 comes along, breaks up the F2 molecule, bonds with one of the fluorines, and now we've got a molecule of our product. How are we going to make the second molecule of our product? Joel? So now, if I put those two together, it is going to give me the overall reaction because I have two NO2s on the left side. I have two NO2Fs on the right side. And I have F on both sides. That's going to cancel out. Also a viable mechanism. Question or another option? All right. Could we have another option? NO2 plus NO2. Well, so I wouldn't make this into 2NO2. If I'm going to combine those, I could make N2O4. So I might combine the two NO2s first, then have N2O4 react with F2. Maybe that just makes one big conglomeration of the two. And then what might happen? Then it could just decompose. The comment was made, maybe you could heat it and then it would do this. Well, in a mechanism, everything's happening under the same conditions. So the idea is, this decomposition might just happen under reaction conditions. So we could have this just breaking up into two molecules. Question, Noah? So the question is, does the arrow on the third step represent heating? No. Sometimes you form an unstable molecule in the middle of a reaction, and it just falls apart. So all of these steps would be occurring sort of in the same reaction mixture. And so you don't need to do different things to make the different steps happen. So the question is, realistically, would there be an actual reaction mechanism? Yes. Generally, most reactions follow a single mechanism. Now, some reactions actually have several options, and so there might be more leeway. They might follow several different pathways. That's certainly possible, but most reactions have a primary reaction mechanism. A chemist, one of their goals in studying reaction kinetics is to figure out what the correct mechanism for a reaction is. All right. The reason we want to know the correct mechanism for a reaction is if we want to manipulate reactions, if we want to be able to use them to do whatever things we want them to do, right? We use reactions to run machinery. We use reactions to make new pharmaceuticals. If we want to be able to use the reactions in all those different ways, then we need to have some understanding of how they happen. So the reason this is under the heading of kinetics is the mechanism that the reaction actually follows has an impact on the kinetics of the reaction. And so by studying the kinetics of the reaction, we can get insight into what the actual mechanism is and understand the reaction. So right now, all we're doing is proposing potential mechanisms. That's often a first step when you're thinking about how a reaction's going to happen. And then you study the kinetics of it and see which actual mechanism, which one is consistent with the experimental results. So the question is, if you have an unstable molecule, can it break up and then go back to itself? Yes. There are lots of reactions, and that's generally going to be an equilibrium where you have a reaction going in one direction and then going in the reverse direction. So stay tuned for that. That'll be our next topic after chapter 14. You can have reactions that go in both the forward and reverse direction. Right now, we're going to focus on forward reaction. But we'll definitely see reversible reactions. Did anyone come up with another potential mechanism here? Okay. So that's a pretty good list. We see, I just want you to get the idea that there are multiple possibilities for how the reaction might happen. Now I'm going to go to a simulation of this reaction. Let's see. Mouse. Um, Lauren, could you hit the lights? Ooh. Put the other switch to the middle. No, the right-hand switch to the middle. There we go. Perfect. Thank you. So here's an actual reaction mixture with NO2, which are these molecules with the dark atom in the middle, and then the two red atoms representing oxygen, and then F2 with the two green atoms. All right. So this is, in this mixture, we're starting out with all reactants. And what it's going to do is it's going to highlight every time a reaction event occurs. So I'm going to go back a couple of frames, and I'm going to zoom in on one of these. All right. Zoom in right there. So these two molecules here are colliding with each other. And see the F2 bond breaks. One fluorine bonds to NO2. But this was a case where it actually didn't happen all the way, and it actually went in the reverse, like Ralph asked about. So notice they come together. It looks like they're going to exchange the fluorine, but then they didn't. So let's zoom out. We'll keep watching. Sometimes you have those reactions where it starts rolling up the hill, doesn't quite make it over to the products. All right. So here we actually have a loose fluorine atom. So this would be the second step in our mechanism. And that loose fluorine atom is now bonding to an NO2. So the mechanism that it turns out to be is this one over here on the right, where NO2 reacts with F2, makes one molecule of NO2F, releases a free fluorine atom, and then that free fluorine atom bonds to another molecule of NO2. So we'll go back and look a little bit more. All right. Let's see if we can catch one in the act. All right. Right up here, we have two molecules about to collide. They react. The fluorine, actually we saw both reactions going on there. So here I have NO2 bumping into F2. It steals the F atom, leaves a free F atom over here, and then that second F atom very quickly is going to add itself to another molecule of NO2. All right. So if we left this sitting here for a long time, what would eventually happen is all of our reactants would get converted to products. Question? All right, so the question is, couldn't the single F atoms bond to each other? The student said F ions, but notice they're not ions here. These are actually forming free atoms with an odd number of electrons. So it is possible that two F atoms could meet up with each other and just reform F2, which would then just go ahead and do the first step of the reaction mechanism again. So that, I'm sure, that event probably would happen somewhere in here. But there's a very low concentration of F atoms at any point in time. And so it's unlikely for two F atoms to actually bump into each other. All right, so the question is, what method would chemists use to figure out this mechanism? And that's why we're going through this whole series of lectures. So that's what we're going to discuss. So right now we're introducing the concept of mechanisms, becoming familiar with the idea. and then we're going to talk about how experimentally we could get evidence to support or to contradict a given mechanism. Yeah, it's a great question. All right. So we have different potential mechanisms. As David brought up a minute ago, if you have a multi-step reaction, you're going to have multiple bumps in the reaction coordinate diagram. Each step is going to have its own activation energy, and generally the highest peak on that pathway is going to represent the slowest step. So this reaction has 3 activation energies. I'll call them EA1, EA2, EA3. Now looking at this diagram, what can you tell me about how fast each of those steps goes relative to the others, do you think? All right. So does the first step take the least amount of activation energy? Yeah, the third step actually has the lowest activation energy. That third step is probably really fast. The middle step is probably the slowest because it is the highest peak. And that first step is probably somewhere in between the two. This would be a reaction where that second step creates something really pretty unstable, and so the third step happens pretty rapidly after the second step. Generally, the highest energy transition state means the slowest step. And I want to point out, after each step, there's a little valley there. The things that are present in those little valleys we call reaction intermediates. The reaction intermediates are the things that get formed in the middle of a reaction, but then used up. So I'll give you an example in the mechanisms we just wrote. So in this mechanism here, F atoms, this is a reaction intermediate. All right. So in addition to recognize intermediates, now it's time for us to talk about catalysts and how they work. Okay. So a catalyst is something that lowers the activation energy of a reaction, but doesn't get used up in the reaction. So a catalyst speeds up the reaction, but doesn't get used up. So here's an example. This is one of great importance, actually, from the tail end of the 20th century. O3, does anyone know what O3 is? That's ozone, all right? Now, it turns out chlorine atoms really speed up this reaction. First of all, let's write the overall reaction. Take a moment, write the overall reaction if you put those two reactions together in that mechanism. All right, what's the overall reaction here? (203 to 302). All right. Doesn't seem like much is happening. But this is the destruction of ozone. This is taking ozone and turning it back into regular old oxygen. There was a problem discovered in the 1970s, 1980s with the ozone layer, which blocks UV, protects us from the sun. The origin of that problem was that we were putting lots of chlorine atoms up into the atmosphere. Those chlorine atoms would catalyze the destruction of ozone, and so holes were opening up in the ozone layer. Since then, we banned chlorofluorocarbons, which were the origin of the chlorine atoms that were going up there, and we've seen a reversal of that problem. So it's kind of a case for where scientists said we need to do this, and we saw a result. So in this mechanism, chlorine here is acting as what we call a catalyst. ClO would be what we would call an intermediate. One way to recognize a catalyst in a reaction is it's going to be there at the beginning and there at the end, but not in the middle. So notice chlorine is there at the beginning, it's there at the end. But in the middle, it's bonded to an oxygen. ClO in this case would be an intermediate. An intermediate is there in the middle. But not the beginning or the end. So you'll notice neither one of them shows up in the overall equation. The overall reaction doesn't have Cl in it, doesn't have ClO in it. But we give them different names. Sorry, question? So the question is about chlorofluorocarbons. Yeah. So chlorofluorocarbons are often used as refrigerants. So they're made of chlorine, fluorine, and carbon. So, you might have a chlorofluorocarbon that looks like this. And they were used as refrigerants because they're remarkably stable, and they have the right thermodynamic properties when they evaporate and whatnot. They also used to be used in aerosol cans as a propellant. Um, the issue is when they get into the upper atmosphere, right? These things are stable in the lower atmosphere, so they get released. Nothing happens to them. They end up floating up to the stratosphere where the ozone layer is, and up there, UV light from the sun can break the chlorine atoms off. So they were like, perfectly stable here at the surface, which was why people were like, oh yeah, this is we can use these. They're not going to break down. They're not going to hurt anyone. But when they got up into the stratosphere, they broke down, and that was the problem. All right, so now I'm going to make an analogy for one way a catalyst can work. All right, we said a catalyst lowers the activation energy for a reaction. And why is there an activation energy, do you think? Where does activation energy come from? All right, generally we have to break some bonds in order to go from reactants to products. So because we have to do some bond breaking takes energy. So what's one way you could make the activation energy for a reaction lower? Make the bonds weaker. All right. So perfect. I need 3 names here. I need a name starting with A. Oh, and look, I pulled Amy's card. Do you want to use Amy, or do you want to use a different name starting with A? We'll just use Amy? All right. All right. I need a B name. Eduardo, give me a B name. Let's actually not use names of actual people in the school. All right, Bob. All right. C. I need a C name. No, let's not use Catherine. I have too many Catherines in AP Chemistry this year. Juliet, give me a C name. All right, Charlotte. Caroline? No, okay, fine. Sure. All right. So, here's the idea. Amy, not this Amy, but a different Amy. Amy sees Bob and Caroline together and is feeling jealous. Amy really wants to bond with Bob and sees Caroline as an obstacle. So Amy really wants this reaction to happen. A plus BC makes AB plus C. All right? The problem is B and C have such a strong bond. So Amy's going to call on her friend. I need a name starting with D. Steven. Devon. All right. All right. Amy calls on her friend Devon and says, Devon, maybe you could start talking to Caroline for me. Maybe you could, strike up a relationship with Caroline. So in other words, Devon's going to come along and start up a friendship with Caroline and make a bond. So now C will be bonded to both B and D. Well, how does Bob feel about Caroline's relationship with Devon? Maybe not so happy. What's going to happen to the bond between Bob and Caroline now? It's going to weaken. All right. So now that bond is weaker, Amy sees her chance. She says, hey, Bob, how you doing? Long time no see. Maybe we could get together sometime. And Bob's like, hey, Caroline's all distracted with Devon. That bond is weaker. So Amy swoops in, breaks the Bob to Caroline bond, and now Amy and Bob are together, and Caroline and Devon go off on their own. Of course they're still friends. Of course they're still friends. All right. No, the crowd says no, they can't still be friends. Now, here's the really devious part, because this is what catalysts do. Devon was never really into Caroline. So now that the reaction's complete, Devon decides, okay, I'm out of here. I've done my job. So this overall reaction, I mean, I already listed it on the first slide. The overall reaction was A plus BC makes AB plus C. Devon was what in this case? A catalyst. A jerk, yeah. Maybe. It all depends on, who you were rooting for in the soap opera. Why is the reaction faster now? The bond that needed to break, the key bond that needed to break, was weaker, so the activation energy was lower. And I'm gonna show you like a real organic chemistry example of this that you don't need to write down. But I figure, instead of just A, B, and C, I'm gonna show you how an actual catalyst could do this. I'm gonna draw fast in the interest of time. Let's see. Yeah, I just want to do one more slide today, I think. All right. So here's an example of a reaction involving an organic molecule. This is an aldehyde. We've talked about skeletal structures before. You may or may not remember exactly how they work, but this is a 2-carbon aldehyde. Now, sometimes water would like to bond with an aldehyde, but this carbon-oxygen double bond is pretty strong, and so water just can't actually get in there and break that carbon-oxygen double bond on its own. So what water does is calls for some help from acid, H+. And what that does is it makes the carbon-oxygen double bond weaker. All right? And again, don't try and copy all this down. This is just an example for fun. Makes the carbon-oxygen double bond weaker. So now what can happen is water can come along and react with this. Water comes along and bonds. Now that the carbon-oxygen double bond is weaker. And then the last step is for H+ to fall off. And so we make a molecule that looks like this. Plus H+. Acid is a really good catalyst in this way because H+ can bond to stuff, weaken some bonds, a reaction can happen, and then the H+ can get released. That's why acids catalyze a lot of different things. So that's just one organic chemistry example where water wants to bond to, in this case, an aldehyde, and the acid catalyzes that. The overall reaction would look like this. It's the aldehyde plus water makes the hydrate, what we call the aldehyde hydrate. And H+ is the catalyst along the way. Okay. So this isn't like just some abstract thing that never really happens in real life. Catalysts work this way a lot. There's another way catalysts can work. I'm hoping next time to read you a poem about that way. That would be enzymes, because enzymes are a little more complicated. In addition to maybe weakening the bonds that they need to weaken, Enzymes actually also sometimes hold the molecules in the right orientation. So the last thing I want to do before we go is just point out, sometimes we have an energy coordinate diagram for a reaction. And I'm going to say this represents the reaction without a catalyst. What would my energy coordinate diagram look like with the catalyst? All right, the peak will be lower. And in addition, there's probably multiple steps. So the key difference is that the peak will be lower, but with the catalyst, there might be, there might be a couple of steps. But the key is the peak is lower. And I think we'll call it a day there.